Well, a very warm welcome to everyone here at Campus Biotech, where the management of the Human Brain Project has its headquarters. We are an EPFL organization, or we are EPFL, École Polytechnique Fédérale de Lausanne, is the coordinator of this project, and hence we are located in Switzerland, where we are an outpost of Lausanne, of the Lausanne campus here, together with our colleagues from the Swiss Brain Project, the Blue Brain Project, a major initiative of the Swiss government and part of the Human Brain Project core technology portfolio. So what I'm going to do tonight in the next 7 minutes, correct, 7 minutes, so I'm trying to do that, get you through a project that has the following key numbers that I'm just going to show you right now. Here, this is our project in just a nutshell. I'm trying to tell you about this in 7 minutes. So it's going to be a little bit of a challenge, but this is your evening, and so the idea is really that you can come back with your questions, and if we need to clarify anything, we'll do that. So rather than just drowning you in information, it's going to give you a taste, and then we can interact, right? That's the idea and the dynamic that we hopefully have tonight. So the project, if you look at this, 800, almost 900 researchers, 700 scientific publications today, and about €1 billion in funding. That's sort of the key numbers. We are not proud of the 31% here, just going to tell you right now. The gender balance in the project isn't where we want it to be. We put it in all of our slides. We put it on the top because it's a priority for us to change that, and we are actively working at that. And not just in terms of getting support functions filled, but actual leadership functions. We're going to have a very clear idea of how we want to achieve that. Just to start out here. So what I'm telling you tonight is basically the following thing. We are building in the Human Brain Project a European infrastructure for brain research. This is essentially what that is. These are platforms that researchers can use to do brain science, to accelerate brain science, brain medicine, and to bring results to the European citizen and the European patient. We'll talk about how this happens during this evening, really how technology really actually gets on the ground. But here's what we're doing. So in a way, you can think about this as a Swiss Army knife for brain science. Now, these are the different tools that you see here. And what we're doing really is we're building those tools on top of an existing European infrastructure in high-performance computing. So what we're doing is bringing together biology and computer science in the most fruitful way possible for brain research. What you see here are essentially the 6 best and fastest supercomputers in Europe. They're networked together in a network called PRACE, and we are building our platforms on top of this infrastructure. We also have down here, and this is another little piece that you will be, those of you who are technologically interested, we see we have 2 neuromorphic systems that we are also, we can also deploy. What does neuromorphic mean? It means that these are computers built like the brain. These are essentially, on the right-hand side, you see an actual analog system. This is an analog computer that is built. The chips are like little neurons. There are like hundreds of thousands of little neurons on those chips, silicon neurons, of course, but basically that's how it works. And the cool thing about this is you can run experiments like learning, like plasticity of the brain on those computers. And the very good thing about it is you don't have to actually do it in biological time. You can accelerate this 10,000 times. So we can look at we can simulate certain things on these very, very quickly. Now, the idea is to bring all of these computers also together in a modular way, so that we also, in addition to doing brain research, we're also pushing the frontier of computing in Europe. Now, of course, if you're saying, well, we're computing things, there's biology involved, there's computing involved, you kind of ask yourself, well, where's the data coming from? What are we actually using? And here's the list of where the data can come from. And obviously there is now, and I don't know if you're aware of this, but neuroscience and a lot of other sciences, biological sciences, are done on an industrial scale. In order to get to where we need to go, in fact, we need to do this very, very large scale. So this is all about scaling up. So there's, for instance, the top one here is one of our partners in the United States, the Allen Institute for Brain Research, and they're really doing kind of like the Human Genome Project. They're doing this on a very, very large scale, and they're producing very large data sets, which we can also use to make our models better, to make our simulations better, and to bring biology into the computer. There are other ways, of course, the regular scientific data sets, but also newer things like wearables, right? So we're talking about wearable technology that takes data from your brain and makes it available to research and to yourself as well. Here's a little bit our roadmap. I'm not going to go into this too much because I think it's a lot of text on here. What I want to just point out to you is that in the next couple of years, we want to arrive at a point where the Human Brain Project is a sustainable European and leading institution or brain research infrastructure that's available to all European researchers and also globally. This is what we're doing for industry. So those of you who are in industry and neurotechnology and other in pharma, that's pretty much what we're doing. We're helping to increase discovery, decrease the risk, and we're providing a number of services. This is like the Human Brain Project in one slide, essentially, for industry. And we start to have those collaborations now. Here, maybe one last bit of information for you. Why is the Human Brain Project such a massive undertaking? Why is it even a global undertaking with our other partners? Well, the problem lies in the complexity of the human brain. We have in our brains about 100 billion synapses, nerve cells, essentially, which each of them have 5,000 to 7,000 additional connections to the others. This makes this an incredibly complex system. This system is not just complex because there is so much of it in the sense of connections, but it also is a multi-level problem. So this is really, it goes from the scale of a micrometer to a couple of 10 centimeters. If you start including other brains interacting, you're looking at meters here. So that is one axis. The other axis is time. We've gone from microseconds to lifetimes, and if you look at evolution, even hundreds of thousands of years. This is the space that we have to work in order to actually understand the brain, in order to actually develop innovative medicines, and in order to develop new technology that is benefiting the citizens. This is the Human Brain Project in a super small nutshell, and I'm not gonna, it's actually a small nutshell, I'm qualifying a nutshell even here, but you can see that there is lots more to talk about. I'm not gonna do this here at this point, but I hope you can ask your questions and we can interact tonight. We'll also be available, obviously, afterwards for networking, for questions and answers. And I really want to, again, warmly welcome every one of you tonight. And I look forward to a really great and productive event. Thank you very much.
Thanks a lot for giving us the opportunity to present here. My name is Marc Oliver Gewaltig, and I have several roles in the Human Brain Project. And I'm trying to explain a little bit. You didn't help myself. Okay, I'm trying to explain a little bit of the strategy that we're using in the HBP for 3 areas, and one we already heard about, namely accelerating neuroscience by tools and technology, accelerating medicine, and also accelerating future computing technologies. And basically these 3 aspects here, they bring together everything that we typically associate with the brain. And the idea of the Human Brain Project was to design collaborative research tools that allow scientists to basically integrate neuroscience data from medical and also biological sources to understand the brain, to understand the human brain and its diseases, and also derive new technologies. We all hear about AI, but of course, no AI currently matches the natural AI, the natural intelligence that we all have. And I would like to start with this idea of integrating everything that we know into computer models and ultimately simulating the human brain. And I will use a little metaphor for that, namely the creation of the first globe. That was done in 1492 by a gentleman called Martin Beheim. And what Martin Beheim did, he used essentially an empty sphere and populated it with the information that he had available about the Earth. So for example, up there you see medieval maps from that time. They are hand-drawn because printing was about to be invented, and he basically took all these maps, he had to scale them and he had to correct them to arrive at the globe that you see here in the lower left. It still survives. If you're ever in Nuremberg or in Munich, you can watch it in a replica or in the original. And on the right side here we see the globe as we see it in Google Earth. And there are 500 years between these two pictures. And that gives you a little bit of an idea of the expectations that we should actually have in understanding the human brain. It took us 500 years to get from a state where we can roughly understand the outlines of the continents to a place where we can actually zoom into the level of streets as we can do it in Google Earth. And also what we have to realize is that the technology has changed. In Martin Beheim's time, if you wanted to know something about a coastline, you had to send out a ship or an expedition. And what we do nowadays here, this is one of the modern satellites that is circling the Earth. They just take pictures from above. And the same revolution is currently happening in brain research, where when I started studying, you had individual neurons probed by electrodes, and nowadays you use whole brain imaging techniques that are able to see what the brain is doing at a grand scale in real time. And basically what we try to do is we use these technologies to build a simulation of a brain. And we start with a mouse brain because it's much smaller, but from a technical perspective, this is still the same technology. So what you see here are brain slices, and the little dots, they are cells. And we use these pictures to estimate where are the cells in our brain. And then there are certain markers that we can inject into brain that basically allow us to color the cells according to their different types. For example, whether they are excitatory or inhibitory cells. These are some of these markers. So basically we integrate different data sets of these types to give us, to start with a crude model of the brain, but the idea is to collect new data and to improve it as we go along, similar to the first globe, which was not perfect initially, but which was improved as time went on. Now, what you see here now is a very crude simulation of what we get out of it. It doesn't really resemble anything that a real brain would do, but it just illustrates the complexity that these data sets alone give us. So this is a full-scale mouse brain simulation, 75 million neurons, but you will say that you don't really know what is going on here because you just see a lot of colorful dots blinking, and this is kind of deliberate because if you want to understand what is happening in a mouse brain, you actually have to understand what a mouse would be doing with its brain right now. So that brings us really to the point that if you want to understand the brain, you need to understand its body. And this is what we are trying to do in the neuro-robotics part of the Human Brain Project. Basically, you want to observe the brain in its natural habitat, which is the body, rather than isolated in a vat. And that, of course, involves not only a brain, but everything that hosts the brain. That comes from simple models of the body, which hosts vision, hearing, smell, touch, all the senses that we have, and which also hosts the muscles and the skeletal system, which will help us to move about, because ultimately the brain has evolved to move somebody's body through the world and make it survive. That's why plants typically don't have brains. And of course we would like to understand the link between this low-level brain simulation that you've seen before and the high-level cognitive features that we are all interested in and would like to understand. Of course, this is only possible if we embed a brain back into its body, because otherwise, who knows what it sees and who knows how it responds to something. And one of the tools that we built for that is the neuro-robotics platform, which is a little video here. where we try to replicate a complex environment in which a mouse would be, and in this case it's actually an animal experiment for stroke recovery that we are trying to model here. And you see the mouse is just reduced to a skeleton because we want to see the muscle activation of the right paw that you see here. And so this is one of our tools in action where we can try to understand the brain in the context of its body, in the context of a complex experiment that we are trying to replicate here. And with that, I would like to thank you very much.
Good evening, ladies and gentlemen. It's a pleasure to be with you tonight. And I was asked to first present myself and tell you what I do. Let me just put that on. It's not a Mac. It's very difficult for me to understand how to work a PC. Huh? It's not good when you're coordinating a medical informatic platform. Okay, I got it. Here we are. So I'm primarily a physician, specialized in brain disease, most specifically actually in epilepsy. And I've been working in France for many years. I decided to come to Switzerland, the Lémanic region, and Lausanne because of this environment that you're aware of here at Campus Biotech, EPFL more generally, and also the University Hospital at Geneva that has been embedded from the beginning in the Human Brain Project from a medical perspective. That's really what attracted me to come here and decide to participate to this project. This is what I do. It's not very relevant for you tonight, but I will argue that for such a project as HBP, 1,900,000 staff, most of them are very smart scientists, and who hope that they will put together all that money, all that science, all this expertise to also help medicine and to interact with hospital, doctors, and patient eventually. Well, I think it's important to have a few physicians who know how the hospital is working, who know the problems you can encounter when you want to get in communication with this world and be able to have access to the data and all the problems that you can encounter when you're dealing with those data. So I'm not going to get into detail for this. Let's move to the brain disease. Just a few words. In Europe, some survey shows that almost 1 person out of 2 have a brain disorder. That makes a lot of people right there, and that probably include myself. Of course, that include relatively benign disorder like migraine. It's still a brain disorder that can be extremely associated with strong handicap in some patients because it's very frequent. And of course there are major brain disorder like dementia, like schizophrenia. But altogether, it's first of all a huge cost, 5% of the GDP in all Western countries, and about 1 patient out of 2. So it's a great challenge. It's a greater course than cardiovascular disease, cancer, and diabetes together. It's really huge, and it's getting even a greater problem with the aging population. Coming to the MIP, the Medical Informatic Platform, it's one of the 12 sub-projects of the HBP, and one of the platforms that Chris introduced. It's very simple in principle. It's supposed to deliver a software that is being installed in hospital, as many as possible, that will allow to collect, prepare, organize, curate, as we said, all the data that could be of interest and that are captured every day in those hospitals for this several hundreds million patients with brain disease in Europe. Some of them getting hospitalized, most of them getting simply through the outpatient clinic, maybe once or several times, but the data are there. And we're talking about hundreds of millions of individuals. Today in research, people and scientists are extremely proud to say we're getting now cohorts of almost 100,000 patients either from a genetic point of view or neuroimagining point of view, and that's great. But here the scale can be of hundreds of millions, potentially. So the objective is to get access to at least some of this data, which at the moment is completely lost. Most of the data are not being used to better understand brain disease and try to find a way to better manage a patient. I'm not going to get into the technical aspect of the MIP unless you have questions thereafter, and on top of that, I'm not an engineer. But the main element, what you have to understand, is that the concept is that the data never leave the hospital, because this is very difficult for regulatory reasons, data privacy, regulation, cultural aspect. Doctors who do not want to share the data or having them sent away in another country or in another hospital. So the only way that we can share such big volume of data as we are looking for with the MIP and with the HBP is to make sure the data stay in the hospital, never leave it. And then to have a complex IT system where from the central node, we can query all the local hospital and send algorithm and retrieve the result, but without having access to the core data at any time, without having to deal with non-anonymized data. And so respecting all the regulatory and also the more cultural or psychological issue we face when we want to share medical data. That's the objective of the MIP. It's already well advanced, but it still faces a number of challenges. And well, we're hopeful that this can bring breakthrough progress in medicine in the future, though it will take possibly a number of additional years to get there. Thank you.
Hello everyone. I'm very pleased to be here today to tell you something about the research on socially intelligent robots that we do at the Uppsala Social Robotics Lab. So I will start with the question, are we witnessing a new robotics revolution? Several reports have stated that robotics is now one of a few technologies that has the potential over the next few decades to have an impact similar to the one that the internet has today. So one reason is that robotics is now moving beyond traditional applications where robots do things that people, humans, can't do or don't want to do. We can see here some examples of robots used for military application, deep mining, the factory. Robots are now starting to be used in socially assisted scenarios. So scenarios where they provide not only physical, but also social support. We can think, for example, of robots used as instructors for children, as companions for the elderly, or therapeutic tools, for example, for children with autism. And we can see here some examples of robots which I think look quite different from the ones we saw at the beginning. And they also are quite different from each other. Some are more human-like, some are more mechanical looking, perhaps some look more like pets, but they share something. They have an appearance which is social, which resembles our own human appearance. So at the Uppsala Social Robotics Lab, our vision is to build robots that learn to interact socially with people. And that means that not only we work with robots that to some extent look like humans, for example, they have a body, a head, or arms, but they are also capable of engaging with humans in social interaction. They're also capable to talk to people, to understand something about them, understand their behavior, adapting to them, or even learn from them. So why is this important? So on one hand, we produce technical advances, so advances in artificial intelligence and new algorithms that allow robots to help humans in different scenarios. On the other hand, since robots now are being deployed more and more in human environments, it's also important to understand how humans interact with these robots. Do they accept them? Do they fear them? And that also leads us to understand perhaps a little bit about ourselves too. So if we follow along these two strands, I want to give two concrete examples of work that we do. So on the technical side, we are interested in building robots that learn from people. And I have done a lot of work on robots that act as tutors, as instructors for children in school. So imagine using robots that promote the students' learning, student engagement by offering social support, and that they also become new tools for teachers to build new scenarios for learning. So within this context where the robot acts as a tutor, it's also important that the robot also learns, so acts as a learner, learns from people, learns to adapt to people. And I'm going to show you a video. Now the sound doesn't work, but hopefully I can talk you through. This is
No, it does work. Great. You are developing an empathic robot tutor with capabilities that allow it to engage in empathic interactions. To enable a robot to respond empathically, we need to model, interpret, and respond to the learner's affective state with appropriate expressive behaviour and pedagogical actions to the current situation. This requires a new channel for expressive behaviour using facial, gesture, and posture recognition, supporting empathy in a learning context and increasing the learner's engagement. The robot assists the learner in completing tasks with a range of pedagogical actions. For instance, if the learner is frustrated or having difficulty with a task, the tutor will present the answer, explain it, and move on.
The symbol is located somewhere over here.
So within this project, the key idea was to build the empathic abilities into a robot tutors. So we use machine learning to learn from human-human interactions and from human-robot interactions in order to build robots that could adapt to students in real time. The idea being that we should really think about humanizing human-robot interaction, building robots that are humane, that are compassionate, that can learn how to adapt to us rather than us adapting to them. And we can connect now to this technical work also by studying how people perceive these robots while we implement these capabilities, these technical capabilities. How do we know? Will they be effective? Will allow robots to be accepted? So we do a lot of work modeling social behavior and emotion in human-robot interactions, both on the human and the robot. And we study how these affect perception of comfort by people, rapport, or perception of trust in robots. So these two things go hand in hand. So this is the final message that I would like to come across. In social robotics, there are two directions that are equally important. On one hand, we build technical advances for robots that can help humans. And then we also study how humans interact with these robots. And also, hopefully, this will help us understand more what does it mean to be human. And that's
it. Machine learning. So machine learning is a topic which is trying to explain how we can get these things, computers or machines. Sorry about that. How we can get them to learn complex tasks, like for example, recognize images of faces, which they are actually better at doing than us at the moment. How can we do that? And we do not do that by telling them a set of rules. If you imagine, do this little exercise right now, how would you describe to someone how you recognize someone's face? That's not simple. No one knows how to actually do that. So how do we teach these things to do that, even if we don't understand it? Well, sort of the same way we learn stuff. We try things out. We do experience things. So we show it lots of examples, and lots of it. And then we have these huge models where we have quite a few parameters that we can then adapt. And that's the way we can do that. So it's really in one sentence, it gives computers the ability to learn without being specifically programmed for the task at hand. Because the problems we want to solve is completely impossible to figure out all the different things that will happen to this machine. For example, an autonomous car. You can never figure out everything that will happen, but still it needs to deal with it, the same way you deal with it. All right, so what do we do in the team? So we try to automate extraction of knowledge and understanding from data. My strategy has always been, and will probably always be, to do core basic research at the same time as we do applied research. I strongly believe in the cross-fertilization between these, and for me personally it's extremely important to see clear use of the stuff that we do. So for that reason we work together with people who understand the particular problems, typically with industries. These are some of the companies we've been working with throughout the years. So the spine there is a company from Linköping called Sectra, a medical imaging company that we work with. And you have the Gripen fighter, which is built in Linköping, where I used to be living. The third one is motion capture. How do you figure out the motion as I keep moving? So this is together with X, it's a Dutch company that is currently selling a lot to the gaming and movie industry. And then the car built on the West Coast, the Volvo, autonomous driving. Currently I work a lot with Autoliv. I'm not sure how many of you have heard about them. They invented the seat belt and the airbags once upon a time. Nowadays they do a lot of active safety. So they know these systems much better than I can ever do. So I work together with them. Hopefully I have something to offer them as well. So how do we do this? We build probabilistic models of these dynamical systems. It's something evolving over time. And their surroundings, because they sit in a surrounding, as Mark was just saying. Everything sits in a context somewhere. We need to understand that as well. And then we developed methods to actually learn these models from data, because everything keeps changing, so we need to adapt and learn. And then we want to use these models. Either the machines or us are going to use them for something, either to understand something, what is happening, or possibly to take action and actually control the thing. Again, you can have autonomous driving in the back of your mind. The car needs to do what you do without thinking about it, but it has its sensors, receiving from cameras, radars, inertial sensors, wheel speed sensors. All of that needs to go in. It needs to be understood within milliseconds, otherwise it's too late. Then it needs to take a decision what to do. So how do we actually do that and put that in the car? So the cornerstones in doing this, the first one is data. Typically we need quite a lot of it. The second one is a mathematical model. So we use math a lot. So what is that? So it's a compact representation of the data that you have, that in a precise mathematical form describes what's going on. And why is this useful? It's extremely useful in the sense of starting to try and provide some kind of guarantees. Not just show one cool example, but actually to be able to deliver something and say, provide some properties. This is going to be stable, for example. Your car, you want it to be stable. You don't want it to just go off the road all of a sudden. And math is a good way of a good language for doing that. The third one is a cornerstone would be the learning algorithms. So again, think of the autonomous car. You have so much unknown in there. You have all the cameras, you have all the radars coming in. There's so much unknown. Where are all the other vehicles? What's their speed? Where are they heading? Why did that person jump out? And so on and so forth. All of that needs to be understood straight away. So how do we do that? By learning all the unknowns from the data. And a key concept, what I believe to be the most important concept to do something that you could claim being smart or intelligent, is uncertainty. How do you actually work with uncertainty? How do you make these things understand uncertainty? We know we're near there. So that's a huge, my take on what is the most important thing to get in there. Not just what we know, but also have some understanding of what we don't know. I'll give you another example, a concrete example that we did recently about modeling the surroundings. So this is, and this is also a kind of theme that I kind of like, the maps. We saw the maps, that was great actually, what's happened over 500 years. That's one map, and when I say map, most of you probably think about the map like that. But there's so many other things we can map, so many things you cannot see. The magnetic field, for example. The magnetic field in here is extremely interesting. It's changing all over the place here. Can I use that? Absolutely. I can use that to position almost each and every one of you, because you probably have one of these, which has a magnetometer in it that measures, that senses the magnetic field. So if I have a map of how the magnetic field is distorted, I can use that. That's actually how a fighter aircraft navigates, for example. Not with a magnetic field, but the same principle. What we did, and we know a bit about magnetics and the magnetic fields, Maxwell's told us that. So we can use his equations, and then we populate them. On top of that, we have these flexible models, and we populate that with data, and we get the model looking something like that. That's the strength of the magnetic field. And then you can use that to position yourself within a couple of meters accuracy, which is commercialized by some of our friends. With that, I should stop that.